Today I'm going to be discussing a topic that has been requested many times by you guys. It is quantum mechanics. Now, quantum mechanics is a huge physics topic and it encompasses loads of different aspects of our daily lives and the microscopic world. But to be honest, we don't have the time to go through everything. So today I'm going to go through one of the most misunderstood concepts, Heisenberg's uncertainty principle. Now, a lot of the time, this principle is explained to people as you cannot know a particle's position and momentum at the same time. And this is because the instruments we use to measure it, like for example photons or electrons, often hit the object, which means we cannot know its specific momentum or position because this electron or photon would actually knock it off of its path or change its momentum. So we cannot use this to work out its specific momentum or location. The problem with this though is that they're explaining the observer effect, not Heisenberg's uncertainty principle. The observer effect is essentially when you observe a particle or something similar, our observations actually change its position, momentum and other characteristics. So that is not Heisenberg's uncertainty principle. The real way we need to look at it is to first understand that particles on the microscopic scale are actually seen as waves. And now I know you may have seen this through the two-slit experiment and the interference wave pattern that's produced, even if it's done with electrons. So this is very well known already, and we know that particles and waves can both behave as one another. But how does this actually play a part in Heisenberg's uncertainty principle? This wave-particle duality can actually be used to explain Heisenberg's uncertainty principle. So let's think of it like doing a short burst of waves. A short burst would require a range of different frequencies, which means we would know where it's going and its location, but we wouldn't know its specific momentum because there's loads of different frequencies. And then you can think of it in the opposite way, but with just one frequency. If we played one frequency for a long period of time, the wave would propagate outwards, which means we don't know its specific location, but we would know its momentum or otherwise its frequency. So how does this actually affect our everyday knowledge and understanding of the quantum mechanic realm? Well, it would actually be able to explain something called quantum tunneling. Essentially, Heisenberg's principle says that we do not know an object's exact position or momentum, but we also don't know its specific energy. This is important because even in places with temperatures as 0 Kelvin, we cannot definitively say that it has zero momentum. Similarly, in open space where there is no matter anywhere, we cannot definitively say that the energy of that area is zero, which can lead to quantum tunneling and in fact the idea of energy but in depth. Another way that Heisenberg's principle can be seen every day is the fact that electrons actually don't collapse into the inside of the atom. The idea that electrons have an unknown momentum and location essentially means that atoms do not just suddenly collapse, because if they got too close to the atom and we did know their location, then the atom would collapse. So essentially all matter everywhere in the universe rests upon this principle. Okay, so what does this actually mean for us? Well, to be honest, it probably won't ever affect us because it is on such small microscopic scales that we won't even see it or even understand what's going on. But what it is important for is quantum physicists who are essentially trying to build a theory that can both combine general relativity and quantum mechanics. An example of this can be seen in string theory, which I'll be talking about in the next video. So make sure to subscribe and comment down below any video suggestions you have for the next video.